Okay. Okay, so we're looking at quadratic reciprocity. The setting for this is, so we introduced this yesterday. We looked at some nice pictures, so I'll flash them in front of you again now, just remind ourselves. But the setting for this is, of course, our Legendre symbol, NP. I've probably written this about 50 times by now. N is a residue, mod P. N is not a residue. Okay, by residue we mean quadratic residue. So the Legendre symbol NP is going to be +1 if n is congruent to a square modulo p, and it's going to be -1 if n is not congruent to a square modulo p. We observed before, I won't do the derivation again because I've done it a number of times, but from the fundamental theorem of arithmetic, understanding how to evaluate NP crucially depends, or it kind of reduces to, being able to evaluate the Legendre symbol QP for primes Q and P, okay? Primes Q and P. Okay, because we can factorize n, looking at its prime factorization. The Legendre symbol is multiplicative in the first instance, so the Legendre symbol of the big product, modulo P, factorizes into the big product of the individual Legendre symbols, where you've got 1 prime modulo another. So the general problem reduces to this special problem, being able to evaluate the Legendre symbol of 1 prime modulo another one. So if you were in the lecture yesterday, you would have seen this diagram, which we generated using some Sage Python code. So what this is showing is, well, first of all, we looked at a plot showing us the +1s and -1s. So these are we're plotting points here at every point of the plane with prime x and y coordinates. Okay? So these are all the points, little p, little q. And we looked at a first plot which showed which ones were +1 and which ones were -1. And while we couldn't spot any particular pattern in which ones were coming up +1 and which ones were coming up -1, we did see that for certain rows and columns, the diagram was symmetric. So then we generated this picture. This picture indicates the symmetry relation across the 45-degree line. So a point over here you think of as is at coordinates PQ. Its reflection across the diagonal is at the coordinates QP. And the meaning here is that the unfilled circle means that PQ has the same value as QP. That should be a comma there, it should be a straight line. Okay. So that the Legendre symbol PQ is the same as the Legendre symbol QP. That's what the empty circle in one of these positions means. The filled circle, the black dot, means that the Legendre symbols PQ and QP have opposite values. Okay, the picture doesn't indicate which one is +1 and which one is -1, but a black dot here at the top left, and it's also a black dot here, of course, at the bottom right, indicates that 3, so the last prime before 200 is probably 199, probably. So 199, so the status of 3, and the first prime is 3, first odd prime, so the status of 3 modulo 199 is the opposite of 199 modulo 3. Okay, so one is a quadratic residue modulo the other, and vice versa, it isn't a quadratic residue modulo the other. Okay? Whereas if we look at the unfilled circle here, this is indicating that the status of 3 modulo 197 is also prime, second dot down. The status of 3 modulo 197 is the same as the status of 197 modulo 3. Okay, we'd have to reduce 197 modulo 3, and depending on whether it's 1 or 2, we'd know whether it was a quadratic residue or not, because 1 is a quadratic residue modulo 3, 2 isn't. But they have the same status, okay? And when we looked at this picture, we noticed that this picture is exactly symmetric. And when you count across the columns, you found the first column was a mixture, the second column was all white, the third column was a mixture, the fourth column, although it's not there because that isn't a prime, the fourth odd integer, but we'll call it all white. The next one is a mixture, the next one's all white, mixture, all white. So the status exactly alternates across the odd integers of all white, mixture, all white, mixture. And if you look at one of the mixture rows or columns, they basically alternate. If you label all the odd integers, okay, it's only the prime positions that are shown. If you label all the odd integers, they alternate exactly. Black, white, black, white, black, white, black, white. Okay. So we've got exactly alternating behavior across all the odd integers. So that suggests we describe that really what we're seeing here is a modulo 4 pattern. Okay, because you've got stuff that alternates across the odd integers. So that suggests that we have a modulo 4 pattern. So yesterday we discovered the law of quadratic reciprocity. Which was that PQ, well, it's either not equal to QP or it's equal to QP. Of course, if it's not equal to, it must mean it's minus of it. Because remember, the Legendre symbol is either plus 1 or minus 1. And they have opposite sign exactly when both of the primes are congruent to 3 modulo 4. And otherwise, they have the same status as each other. Okay? And that's the kind of surprising thing or the remarkable thing from the law of quadratic reciprocity, that there's some relationship, because remember, every prime is congruent to 1 or 3 modulo 4. If you're looking at pairs of primes, there's 4 possibilities. Each one on its own can be 1 or 3. So the two together, there's 4 possibilities. 3/4 amount of the time, they have the same status. And 1/4 amount of the time, when they're both 3 modulo 4, they have opposite status. So that suggests there's a strong connection between that's forcing primes to have similar residue status modulo each other. Because if it was just a random, if the chances of P being a residue modulo Q were independent of the chances of Q being a residue modulo P, we'd only expect to see them agree 50% of the time. Like flipping 2 independent coins. You only expect them to turn up the same value 50% of the time. Is that correct? Heads, heads, tails, tails, head, tails, tails, head. Yeah, 50% of the time, they turn up the same value. But they don't. 3/4 of the time, they turn up the same value. 1/4 of the time, they land opposite. So that suggests there's strong connection between the residue status of one prime modulo another and vice versa. Okay. I'm postponing the proof, so I want to look at this result and look at applications of it before we kind of slowly, or we give some of the justification for why it's true. Remember, all we've seen so far is some evidence that it's true amongst the first primes between 3 and 200. I mean, who's to say that the pattern doesn't break down when you look at larger primes? Hey, it doesn't, but you can never prove it just by looking at those and those graphs, okay? So there's an infinite number of primes. So there's a proof of quadratic reciprocity in the book, and we'll certainly do some description of it. But for now, let's look at applications. So the first key applications, the first key application was we've now, from this, we've got an algorithm for calculating arbitrary Legendre symbols. Okay? Because we've got this factorize, flip, reduce. So I squeezed in a quick example of this at the end of yesterday, but I'll show you another example now just to reiterate the principles. So this is our factorize, flip, reduce algorithm for evaluating NP. So you just do these 3 steps. You factorize, you flip, and reduce. You start wherever appropriate, but you do them in this order. Factorize, flip, reduce, factorize, flip, reduce, factorize, flip, reduce. And it will produce a series, a growing collection of Legendre symbols, but the modulus will be getting smaller all the time. And eventually it'll be modulus 3 or 5, and you'll be able to just decide by inspection what the value of the Legendre symbols. Multiply them all together and you'll get the value of this. So consider 161. Okay. So the question is, does there exist an m such that m squared is congruent to 100 modulo 61? That's the question. Is 100 a quadratic residue modulo 61 or not? I don't know. Yeah. Okay. So we're going to factorize, flip, reduce, factorize, flip, reduce. Now, which bit do we do first? Well, someone whispered factorize, but that's not the right answer. The 100 is a bit too big, really. There's a better representative of 100 modulo 61. We should reduce first. Yeah. Reduce. Because it isn't really a question about. Yeah, you start wherever is appropriate. We could factorize at this point, but I think it's better to reduce because we can. Because really it's a question about the congruence class of 100 modulo 61. So it's really, it looks slightly simpler like this, okay? So it's this Legendre symbol is equal to 39, the Legendre symbol of 39 mod 61. So that's reducing 100 modulo 61. Okay, but now we go into factorize. Okay, 39 is not a prime number. 3 times 13. So it's the product of these 2 Legendre symbols. And neither of 3 or 13 are squares, of course, they're both primes. So it's not immediately obvious whether 3 or 13 are quadratic residues modulo 61. They could be or they might not be. Okay. 61 is too big. I mean, I could use the brute force naive method. I could square everything modulo 61. So I'd have to square the first 30 congruence classes. Remember, you only have to really square the first half of the congruence classes, because the second half are just the negatives of the first half. So they will go to the same values as the squares of the first half. But I'd have to calculate 30 squares and inspect the list to see if 3 was on it to determine that way if 3 was a quadratic residue modulo 61. So I'd like to keep going. So we've done a factorize. Let me do a flip. So now we make use of the principle of the law of quadratic reciprocity. So these Legendre symbols can flip. Because there's a strong relationship, and we understand exactly how it works between the residue status of one prime modulo another and the vice versa version. So I flip these. It's 61 modulo 3 and 61 modulo 13. Now I might need to bring in a minus sign. Okay, because they're only equal. Okay, I'm assuming they're equal there the way I've written it down. I might need to make additions to it. They're only equal 3/4 of the time. But if it happens that both of the primes are congruent to 3 mod 4, then you need an extra minus sign, okay, because they have opposite states. But of course, well, 3 is congruent to 3 mod 4, but 61 isn't. 61 is congruent to 1 mod 4. 60 is a multiple of 4. So there's no extra minus sign needed. Okay? So both of them flip like this by quadratic reciprocity, by the LQR, the law of quadratic reciprocity, and the fact that 61 is congruent to 1 mod 4. Okay, so they're not both 3, so we don't need any minus signs. We factorized, we flipped, we reduce again. Okay? Because the 61 modulo 3, well, what is 61 modulo 3? It's 1. Yeah. 61 divided by 3 leaves remainder 1. What is 61 modulo 13? It's not so easy. 4 times 13 is 52. 9. Okay. So we reduced. Well, things are, we can say, I mean, I could keep going, factorize, flipping, reducing, but I think we're at a position now where we should announce, we should start evaluating. Okay. So my original Legendre symbol is now a product of these two much simpler Legendre symbols. And what can we say now? Say something sensible now about those Legendre symbols.
They are both plus 1.
Okay, why are they both plus 1? Why is 1 modulo 3 plus 1?
1 squared is 1.
Okay, 1 is always a quadratic residue. 1 is always the square root of 1, no matter what the modulus is. So that is definitely plus 1. And 9 modulo 13?
3 squared is 9.
3 squared is 9. So 9 we recognize as a square integer. Okay? It's not some funny effect of modular arithmetic that this thing is a square modulo this. It's just we recognize it is a square because it's a square integer, the square of 3. Yeah, the congruence class of 9 will always be the square of 3 no matter what the modulus is. So we got a little bit lucky. We encountered a square integer that we could recognize as a square, so that's clearly plus 1.
But it's not bigger than 6 or 1.
So 1 and 9 are both quadratic residues. Irrespective of what the modulus is, but in particular, modulo 3 and modulo 13. So plus 1, so it's plus 1.
So why did you choose plus 1 for the second one? Because it's 3.
For this one?
Yeah.
Because remember, what are these Legendre symbols? They are it's an indicator function for whether n is a quadratic residue modulo 3.
Oh, okay.
So is 9 a quadratic residue modulo 13? Well, yes, straight away, because 9 is the square of 3.
Okay.
So it is congruent to 3 squared.
So we put plus 1.
So plus 1 for that. Yeah. So this one's plus 1, this one's plus 1. So the answer to the question is yes. 100 is a quadratic residue modulo 61. Now, unfortunately, this is one of these funny things in mathematics that we often have existence proofs, but which are non-constructive. So it's answered yes. It says there is a square root of 100, modulo 61, but it provides no help really in finding it. Okay, so that's an entirely different question. finding a m such that m squared is congruent to 100 modulo 61 requires further work. In terms of what we've described, I think we probably just would have to resort at the moment to trying everything. Testing all the numbers between 1 and 30, because they're the first half of the elements modulo 61, and looking for which of them squared gives us 100. Yeah. So that's another example of our factorized flip reduce. Any questions about it, or any queries? To me, it's quite reminiscent of some of the principles involved in the Euclidean algorithm. Euclidean algorithm replaces questions about GCD of large arguments with questions about GCD of smaller arguments. You keep on applying that until the arguments are so small that the answer is obvious. In particular, remember the way we fully analyzed it after your last integer division, you're saying the GCD of something with 0. And that's obviously what the sum is. Okay. This is a similar question, replacing Legendre symbol with large arguments with Legendre symbols with small arguments. And eventually they get so small that we can just answer straight away. Okay. If it hadn't dropped out as an obvious square modulo 13, if it had come out as 10 modulo 13, well, we could have flipped that again, reduced the 13, flipped again if necessary, reduced. Just kept going until it was something that we could have added. Yeah. Or recognize as a square. So factorize, flip, reduce. Good. Okay. So I'd like to jump now to another application. So this is actually in the book. This is example. So I'm hopping around a bit in the notes. I'm skipping some of the lemmas and that go towards the proof of quadratic reciprocity. So I'm jumping towards some of the applications. So we'll have a look at example 8.4.
Oh, yeah, no. Romanesque broccoli. That's what it was. The cauliflower.
So example 8.4. Recall, we've already determined the status of -1 modulo p. +1 for p is congruent to 1 mod 4. -1, p is congruent to 3 mod 4. We've also determined the status of 2 modulo p. We've figured out what the status of 2 is because, well, I think I stopped just right before the end, but I encouraged you to finish the derivation. I mean, it's explained in the notes. When p was congruent to +or-1 modulo 8, and it was -1 when p is congruent to +or-3 modulo 8. So like in some of the initial investigations we did of quadratic residues, we worked out all the quadratic residues modulo the first few primes, and we remarked, oh, look, sometimes that 2 is a residue, sometimes it isn't. We didn't go very far. I mean, maybe if we'd been very methodical and done the first 200 primes, we could have tracked when 2 was occurring as a quadratic residue and when it wasn't. Maybe we would have picked up on the pattern of +or-1 mod 8. Yeah, maybe not. I don't know. Pick up on a pattern of +or-1 mod 8. I don't know. That mightn't be so easy. We probably would have picked up on the status of -1, maybe. But anyway. But so those results confirm there is a definite pattern to the occurrence of 2 as a quadratic residue modulo prime. It just depends on the status of the prime modulo 8. And it's like, even if the prime is huge, has loads of digits, as long as you've got all its digits, determining its status modulo 8 is quite easy, because 8 is 2 cubed, so everything, so 1,000 is a multiple of 8. So it really only depends on the last 3 digits, the hundreds, tens, and units. You can work out the status of something modulo 8 just by dividing its least significant 3 digits by 8 and seeing what the remainder is. Okay, the thousands and higher, they're a multiple of 1,000, and 1,000 is divisible by 8. So we can use quadratic reciprocity. Now, those came from, we proved those using Euler's criterion, which was that np was always congruent to n to the power of p minus 1 over 2 mod p. Okay. The minus 1 mod p was just a direct application of that. Proving the 2 mod p case, we have to be a bit clever and consider products of all the even congruence classes in 2 different ways. But our law of quadratic reciprocity can help us get similar results for other examples. Okay? We can apply the law of quadratic reciprocity to figure out, in a similar way, figure out the status of 3 modulo. So we'll do it. So what is 3 mod p? Well, we kind of try and use our similar status of factorize, split, reduce, factorize, split, reduce. Well, you can't you can't reduce it. We'll take it for granted that p is a prime bigger than 3. Yes, assuming p is bigger than 3. So you can't reduce it, you can't factorize it because 3 is a prime, so we got to flip it. How do we flip it? We flip it using quadratic reciprocity. Okay, so it flips to p3, but it might be minus p3 or it might be plus p3. Yeah. It was minus p3 in the case where both of the primes were congruent to 3 mod 4. Now 3 is obviously already 3 mod 4, so it's minus p3 if p is congruent to 3 mod 4. And it's plus p3 if that's not the case. What do I mean by not the case? If
P congruent to 1.
Exactly. P congruent to 1. Every odd prime is congruent to 1 or 3. So if it ain't 3, it's got to be 1. And, okay, so it's either minus p3 or plus p3. But what is p3? The Legendre symbol p3. Who can tell me what that is? In a similar spirit to, we were analyzing everything depending on the congruence class of the prime. So how would you describe that? Well, what do we do when we're faced with Legendre symbols? It's another thing you got to paint on the ceiling of your bedroom, just right above your head. Factorize, flip, reduce. Factorize, flip, reduce. Okay.
We all do something.
We don't flip it because we've only just flipped, so we're not going to flip again. We'll just get back to the start. Okay. We can't factorize because it's a prime, so it won't factorize, but we can reduce. P is bigger than 3. So we can reduce it. Okay, but we don't know what P is, but what are the options? What is it going to reduce to? 1 or 2, yeah. Mod 3. Or if P is congruent to 2 mod 3. And which one is plus 1 and which one is minus 1? One is plus, yeah, because if it's congruent to 1, 1 is always the square of 1. Yeah. So that's your plus 1 and that's your minus 1. So what have we got? We've got all the data there, but we try and consolidate it now and summarize it, right? We've got two classifications of P, two binary classifications of P. P is this or that mod 4, P is this or that mod 3. So really, there's 4 cases, yeah? You're looking at P 2 different ways, and in each case, there's 2 values. So there's 4 possible scenarios, yeah? Four possible worlds. Modulo 4 view, the modulo 3 view. And this is all P, so you're either 1 mod 4, 1 mod 3, 1 mod 4, 2 mod 3, 3 mod 4, 1 mod 3, 3 mod 4, 2 mod 3. And we can say what the Legendre symbol is in each case. And if they're both 1, then it's plus P3, and P3 is plus 1, so that's plus 1. If it's 1 mod 4 but 2 mod 3, then it's 3P is P3, but P3 is minus 1, so it's overall minus 1. But if you're 3 mod 4 and you're 1 mod 3, 3P is minus P3, and P3 is 1, so it's minus 1 again. But if you're 3 mod 4 and 2 mod 3, that means 3P is minus P3, but P3 is minus 1, so it's minus minus, so it's plus 1. That's good. We still want to see a 50-50 split between worlds where times when 3 is a quadratic residue mod P and times when it isn't. Because it should be kind of random. It should be evenly distributed. But is there some way that I can join these 2 descriptions? Modulo 4 and modulo 3. Well, it's described in the notes.
She hadn't looked at
You haven't looked at the notes.
I told her she was wrong, and then
So what's the way?
I
Well, it's one of our other named theorems. Okay, we had another named theorem which allowed us to join together simultaneous statements modulo different moduli. With simultaneous congruences with respect to different moduli, we could join them together and move to a higher modulus. Higher moduluses, smaller moduluses project on, no, it's the other way around. Less of these, so many must project. Yeah, large moduli project down onto smaller moduli. So we can use the Chinese remainder theorem. I mean, we can just do it in our heads, but we don't need to go to the formulae, the general case of the Chinese remainder theorem. But the Chinese remainder theorem assures us that mod 4 and mod 3 talk really is modulo 12 talk. Okay, modulo the product. So if you specify something modulo 4, at the same time specify it modulo 3, what you're really doing is picking out a unique congruence class modulo 12. Yeah. Now what are the options for P modulo 12? What can P be modulo 12? Or what can it not be? I mean, it can't be 2 mod 12, 3 mod 12, 4 mod 12, 6. It can't be any multiple of 2 or 3, because any multiple of 2 or 3, modulo 12 will be divisible by 2 or 3, okay, because 12 is divisible by 2 or 3. So we have to avoid the obviously composite congruence classes. So P can only be congruent to some of the potentially prime congruence classes, which are 1, not 2, not 3, not 4, but maybe 5, not 6, but maybe 7, not 8, not 9, not 10, but maybe 11. So every odd prime bigger than 3 must be congruent to one of those 4 modulo 12. And yeah, there's 4. We already said there's 4 possibilities listed here. There's 4 rows here. So each of these rows is one of those options. Each of these rows is one of those options. So really it's modulo 12. So, well, if you're 1 mod 4 and 1 mod 3, I think it's no surprise to find that you're 1 mod 12. Well, let's go through these. If you're 5 mod 12, you see, if something is 5 mod 12, to divide it by 4, well, you see the multiple of 12 bit is already divisible by 4, so you just divide the 5 by 4 to get 1. 5 is 1 mod 4, but modulo 3, it's 2. So the 5 is the case 1 mod 4 and 2 mod 3. So that's the 5. The 7 is 3 mod 4 and 1 mod 3. So that's the 7 case. And the 11 is got to be the last one. 11 is 3 mod 4 and 2 mod 3. So that's the 11. So we end up with this nice, concise expression for 3 mod P in the same spirit as the ones we had for -1 and 2. Yeah. So that finishes this bit. So status of 3 modulo P is +1 in the case that P is 1 or 11 modulo 12, or an easy way to state that is 1 or -1 mod 12. And it's -1 when P is congruent to 5 or 7. Or a convenient way to say that is +or -5 modulo 12. So the status of P comes down to the status of, the status of 3 comes down to the status of P modulo 12. And even though no power of 10 is a multiple of 12, and even if P has a huge number of digits, I mean, it's still a quick calculation to figure out the congruence class of P mod 12, because you just divide P by 12 and see what the remainder is. And even though a number might be huge, dividing it takes as long, it only depends on the number of digits, not the actual size. Even though something might be gazillion, 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 there's still probably just a few hundred digits in it. So it's a relatively quick calculation to work out its congruence class modulo 12. Okay. So we suddenly understand the status of 3 modulo P. So in fact, that would have quickened our argument somewhat back here, part of it anyway. When we got to this stage, the status of 3 modulo 61, we would have immediately been able to say that because we could just work out the status of 61 modulo 12. So 61 is 1 mod 12, isn't it? 60 is multiple of 12, 5 by 12. So 3 mod 61 would have been +1, which we found out that it was, but we could have told that at that stage using our results about the status of 3. So that's another good application of quadratic reciprocity, and it has loads of applications as well. Yeah, one interesting one, which is we won't do the exercise now, but looking ahead to exercise 8.5. Question 3. This is all about special cases of an important result in number theory called Dirichlet's theorem. or which sometimes goes by the descriptive title primes in arithmetic progressions.
What or this?
Dirichlet's theorem. It isn't a theorem in the note. It's like an advanced theorem. You need a lot more. You need some analytic tools, a lot more stuff to prove it. But Dirichlet's theorem says in any arithmetic sequence, progression is like a more, I don't know, more fancy word for sequence. Arithmetic sequences are pretty simple. Remember, we studied some of those in maths fundamentals. A plus NB. N was the index, 1, 2, 3, and so on. Right? Dirichlet's theorem says these have an infinite number of prime numbers. Now remember, we proved very early on, the first initial page of chapter 3, we started proving there was an infinite number of prime numbers. Okay?
Arithmetic
Progression. Just but it's just you often see this phrase used in relation to Dirichlet's theorem. Progression is just in the name of a sequence, something in progress. Yeah, we proved there's an infinite number of prime numbers, and what Dirichlet's theorem says is the prime numbers are really everywhere. You will find them in. You will find an infinite number of them in every arithmetic sequence, except we need a condition. Provided, so in any arithmetic sequence, there are an infinite number of primes. Except it's not true of every arithmetic sequence. There's a condition needed on the parameters. Because some arithmetic sequences are composites. They consist really of all composite numbers. You see, if A and B had a common factor, then let's say it was 3. 3 was a common divisor of A and B. Then every element of that sequence would be divisible by 3. But maybe the first one might be prime. Yeah. A was -3 and B was 6 or something. Yeah. But like if A and B have a common divisor, every element of that sequence will be divisible by that common divisor. So they won't all be prime. They'll all be composite. So we just have to rule that out. So provided the sequence is not an obviously composite sequence, so provided A and B have a greatest common divisor of 1, Dirichlet's theorem says you will find an infinite number of primes in that sequence. Well, you won't because you're going to die soon, but theoretically, you might, well, potentially, I mean, we're all going to die soon. Sorry to break it to you. Sorry to break it to you.
I was saying that for a second.
And then I just heard, no, you're going to die.
I mean, it's a sobering thought. I think about it every day. I mean, it is. You can't get around it.
Yeah, no,
But,
Yeah.
but it's an important thing to think about in terms of constructive stuff, and people take different philosophical approaches to mathematics. Some people are very constructive and only attach importance to things that be constructive, but then there's obviously finite limits on that. Now, we can't prove this theorem in this course because it relies on some advanced tools, but what we can do is settle some special cases of it. So in exercise 5, we deal with some special cases. Special cases that are available to us and susceptible to our tools are the case 4n minus 1, 8n plus 3, and 6n plus 1. So there are some, so all of these fit this condition that the two parameters are co-prime. And And Dirichlet's theorem says, well, all such sequences have an infinite number of prime numbers. We can actually prove directly using simpler tools that these have an infinite number of prime numbers. And there's some guidance given in the exercise 3, and some of these cases exploits the notion of quadratic residues and so on. So this is something to look forward. We'll discuss these in a future class or a future tutorial, but it's something to look forward to. And Dirichlet's theorem is kind of the reason why some people say that like the primes are everywhere, or the primes are homogeneously distributed amongst the integers. They obviously avoid certain obviously composite arithmetic progressions, but in all the other ones, which are not obviously composite, in all the other ones you find an infinite number of primes. So the primes don't avoid any of them. Okay. We'll leave it there for this evening and pick up on it when I see you next week.